I would like to conclude this tutorial with a third module where I will tell you a little bit about the lesson learned from vehicle-to-grid demonstration projects here in Denmark with a specific focus on battery degradation. My name is Mattia Marinelli. I'm associate professor here at DTU. I'm responsible for the research section on e-mobility and prosumer integration. In this module, I will discuss the following points. So first, I will give an introduction on some of the research projects that have been behind the results that you will see in this presentation. A little bit on V2G and V2H. What's the meaning of this acronym? What's the difference? Some examples from activities on frequency control with V2G bidirectional chargers. Their implication from a degradation point of view, so the implication of having this type of service on the battery lifetime. The demonstration activities that we carried out in order to quantify and validate the degradation models that we have been developing and refining here at DTU. And finally, some new possible business opportunities for bidirectional charging with specific focus on vehicle-to-home application here in Denmark. And I will wrap up with some lesson learned and future prospects. I would like to mention three research projects that are now concluded that has been behind the results in this presentation. The first one was the Parker project funded by the Danish funded project, which ran for 3 years. It was concluded a few years ago. It was one of the first demonstration projects with bidirectional charging on a commercial basis here in operating in Europe. Then the ACES project that was also funded by Danish funding. We carried out some of the activities that were defined in the Parker project, specifically on the operation of the bidirectional chargers, but also quantification of the coincidence factor of domestic charging of vehicles, and started a long campaign on degradation measurement, specifically from the vehicles that have been fulfilling these vehicle-to-grid services. Concluding with the ACDC project that Christian previously talked about, where the main focus has been the development of autonomous and distributed charging technology, but along the lines we also continue some of the this long-term degradation measurement also throughout this project. The first thing I would like to mention before getting into the technicalities, V2G and V2H, quite often it's a little bit confusing because you can find a lot of acronyms, and some people give a specific interpretation, other people give a different interpretation. But I think the most, let's say, commonly agreed interpretation is that V2G stands for vehicle to grid, which practically implies a bidirectional power flow with power that can be either taken from the grid or fed into the grid. There can be different control objectives or different purposes in order to have this kind of bidirectional flow. One, which is the one that I will tell you a little bit more about, it's a frequency service, but it's not just about frequency service. You can also use the vehicle to perform more simple, so to speak, price arbitrage or price arbitrage with renewables, where you basically take advantage of the fact that electricity price may be expensive during the evening and it may be very cheap during the night, or it may be cheap during the day if it's coupled, for example, with a photovoltaic plant. Vehicle to home instead, from a technological point of view, it's very similar to the vehicle to grid, but from a controlling point of view, the objective is to limit the power fed back into the grid to a value equal to 0. Meaning that if the vehicle is discharged, it's going to be discharged just to cover local grid-connected consumption from a household. This is different from a V2L or vehicle to load, where the vehicle is capable of supplying some standalone equipment. Also, in this case, there can be different objectives. Frequency control is definitely not one of those, but there could be something that is along the line of the price arbitrage, but more specifically as a time of use where you take advantage of consuming or charging energy from the grid when it's cheap, and then you use the energy during the evening to cover for the consumption. Now, how can we use the vehicle, or how can the vehicle be interfaced with the grid? We have to remember that we have basically two options. The first one is by using the type 1 or type 2 AC plug, which give us access to the onboard charger. And then by having an external controller, charge controller, we can actually modulate the charging power of the onboard charger. So what you see outside, strictly speaking, is not a charger as such, it's just a controller, a bunch of measurement and protection devices. The amount of power that can be handled by this charge controller, it's of course very much related with the capability of the onboard charger. It can be a one-phase, it can be a three-phase charger. The power can go from 6 ampere, which is the minimum specified by the standard, up to practically 32 ampere. And nowadays, no cars really go beyond 32 ampere anymore. Otherwise, it can be used DC port. And while the DC port nowadays, let's say it's more intended as a fast charging capabilities, in the early days when let's say at the time there was only the CHAdeMO protocol and the CHAdeMO plug implemented, it was intended more as a way to use the battery of the vehicle just as a battery, so to charge or discharge it. In that case, the conversion, so the converter itself, it's actually outside of the vehicle. This one that you see in the picture is the one that has been used in the demonstration that I mentioned. This is fairly large and, let's say, not very recent technology. It's a 15 kilowatt bidirectional charger, but of course it can be scaled up depending on the power needs. Then what, for instance, getting a little bit closer to the frequency control, how can we use the vehicle to provide frequency control? From a practical point of view, you don't need a bidirectional charger to provide frequency control. I mean, if you have a bidirectional charger to provide frequency control, of course you have a fairly large range, because you can go from a negative power value to a positive power value, depending if the frequency is below 50 Hz or 60 Hz or above 50 or 60 Hz. And then you would just modulate the consumption or the production of the vehicle according to, for example, a proportional, so a droop characteristic. But you can also provide frequency control also if you have just a standard, let's say, unidirectional charger. In that sense, you can start the charging process with an average current value, for instance, at 11 ampere when the frequency deviation is at 0 millihertz, and then you can modulate down the consumption if you want to provide an under frequency support, or you modulate up the consumption if you want to provide an over frequency support. But now let's focus on the bidirectional charging operation and also some experience from the demonstration activities that have been taking place in Denmark. So practically there has been quite a good number of vehicles. It was mostly Nissan Leaf and a few ENV 200 that have been operating both inside Copenhagen, inside the municipality of Frederiksberg, and on the island of Bornholm since 2016 and 2017. And it's still operating nowadays to fulfill bidirectional frequency service through bidirectional charging. So practically the droop characteristic that is implemented on those chargers follows the one that you see in the slide here, when you have almost maximum consumption close to 9 kilowatt when the frequency is at 49.9 Hertz. Then it's around 0 kilowatt when the frequency is 50 Hertz, and then it goes to minus 10 kilowatt when the frequency is at 50.1 Hertz. The one that you see on the right, it's just an example of how the operation of 10 of these chargers is performed. So you see on the first plot the frequency measured on a 1 second basis. The plot here is reporting 10 minutes, so it's 600 samples. And the power value, so the requested power that the controller is requesting to the aggregation of cars, and the power that is being provided by the cars themselves. If you are interested in having a little bit more of an understanding on the stability implication of this type of control, I would suggest the reference that you find here in the slides. But now let's focus more on the economic and also the degradation perspective of this type of operation. What you see reported in this slide is a little bit of a longer period of operation. So in this case, you see a historical value of 14 hours, which is, let's say, a standard daily operation of these vehicles. I didn't mention that the vehicles are operated during daytime by the municipality employees or by the utility employees to perform their duties, and then when they come back to the garage in the afternoon, in the late afternoon, they are connected to the grid and they are performing this type of bidirectional service. So here you see 14 hours of operation. The frequency is the first plot. The power is on the second plot. You can clearly recognize that when the frequency gets higher, then the car tend to charge more, and when the frequency is getting lower, then the cars tend to discharge, and this kind of consumption and production keep on running continuously. Now, there are a few things that are quite crucial, both from an economic but also from a degradation point of view, but also from a management point of view. The frequency that you see here, so the 14 hours that you see here, are a very, let's say, lucky situation, because you can see that the state of charge throughout the 14 hours of operation has been almost constant, because in the end the amount of charging and discharging have been more or less the same, plus there has been enough charging to cover for the losses of the system. However, one have to take into account a few things. The first one, these chargers, which are, as I mentioned, not very new, they are characterized by a very poor efficiency value when the power is very low, so around 0 kilowatt, which is basically the point where you switch from charging to discharging, the efficiency drops significantly. And unfortunately, for this type of frequency control, normal operation, as a matter of fact, that's where the car or the charger will end up working most of the times. You see here the count of the frequency value in this plot, so it's almost a Gaussian distribution. So most of the time the frequency will be here. That means that most of the time the power operation of the charger will be around this value. That does not mean that you can't take any, let's say, smarter operation of the charger, especially if you have an aggregation of chargers. But if you deploy, let's say, the same control approach on all the chargers, this is the type of response that you will experience. This is one aspect. The other aspect is that the frequency is definitely not balanced hour by hour. It's, let's say, balanced throughout the day at best. And that means that you may have hours when the frequency can be above 50 Hz or below 50 Hz for a good amount of time. And that means that if you're not careful, your state of charge after a few hours could easily cross the boundaries of the car being either fully charged or fully discharged. That practically means that then the car cannot be operated anymore or cannot guarantee the same level of operation towards Energinet, so towards the transmission system operator. That means that you need to be cautious and you need to take a little bit, let's say, not beat the overall power capability of your charger into the management of the bidirectional chargers, but you need to keep a little bit aside. So for instance, if you consider a 10 kilowatt charging and discharging capability, we proved that if you set aside 3 kilowatt to correct your state of charge, then you are basically good to go 365 days a year, and you will be able to correct your operation and keep the car connected and operational throughout the whole period. This has also quite a pragmatic implication, because since this type of service is paid by power committed, then of course you are committing 70% or 69% in this case, compared to the power that you could potentially commit. That means, of course, that the revenue will be impacted. The other item to consider, again from an economical point of view, is that there is a cost, of course, associated with the losses, because as we saw in the previous slide, the losses are fairly significant in this bidirectional charger. And if the cost of the electricity is not small, then the losses can be very high and potentially can basically eat the whole revenue, which in principle could be in the range of 1,000 euro per year. Now let's go a little bit deeper on the implication from a degradation point of view, because I mean this type of operation can be quite stressful for the battery. So over time, we try to understand how much will this impact the lifetime of the battery. So what we did was to set up a series of battery capacity measurement campaigns in different places, on Bornholm, in Frederiksberg, where the cars are located, and also in our EV lab at the university campus. And we demonstrated this kind of approach on several vehicles. Of course, the one that were involved in the demonstration, so the 24 kilowatt hour ENV 200, the 30 kilowatt hour, let's say the second generation of the Nissan Leaf, and also the recent versions of the Nissan Leaf, including my own Nissan Leaf E+. First, I would like to show some of the results from the measurement campaign that we carry out almost throughout 3 years on the cars in Frederiksberg. So the curves that you see here are reporting the measurement that we did every 6 months on the cars, while the continuous line represent the expected outcome in terms of state of health of the projected by the simulation model that we designed here at the university. So let's say on one end, it's clear, it can be recognized that there is a degradation, of course, on those cars. The positive thing is that that degradation it's not so large, or at least considering that the technology, specifically the chemistry, which is LMO, so lithium manganese oxide, which is not very robust against degradation, the cars have not been degrading too much given the amount of time. The other thing is that the degradation measurement are, let's say, well aligned with the trend displayed by the model. One thing that I want to stress is that even though these cars that you see displayed here, they don't drive that much throughout the day. So the municipality that they drive is fairly small, so it's less than 10 kilometers per day. But practically, the bidirectional operation has an impact that is equivalent to a driving usage of almost 100 kilometers per day, which practically means that the cars are experiencing one full cycle charging and discharging every day, which for an electric vehicle, it's quite a lot. Normally, I have some examples later, but normally with an electric vehicle, under normal driving behavior, you will experience something that is probably 1/4 or even less of a full cycle per day. But even under this condition, as we will discuss in a short while, then the calendar aging still remain the main driver, even under such heavy workload. Now, getting a little bit deeper into lithium-ion batteries. So lithium-ion batteries are formed, of course, by a cathode, an anode, and there is an electrolyte. Then the different composition of the cathode and the anode defines, of course, the energy properties and also the degradation properties of the battery. Most of the time, anode is based or heavily based on graphite carbon, while instead the cathode tends to be much more variety in the type of elements that have been used. The lithium cobalt was one of the first. Lithium manganese oxide was another option, which was quite popular, I would say, in the first electric vehicles. Nowadays, it's mostly NMC, so nickel manganese cobalt, and NCA, so nickel cobalt aluminum, and LFP. Just to give you an example, you see here a different composition of chemistries, where you have highlighted also the amount of the individual elements, so the cobalt, the manganese, the nickel, lithium, iron, and so forth. As a matter of fact, when you look at the lithium-ion battery, the amount of lithium is not actually the largest element, but quite often, especially for the NCA and NMC, it's the nickel that dominates. But anyway, in any case, regardless of the composition, it's important to stress that there are different lithium-ion technologies, and they tend to have, of course, different behavior from an energy, but also from a degradation point of view. Focusing a little bit on lithium iron phosphate and NMC, also to stress the difference. You see here on the left an example of an open circuit voltage characteristic of lithium iron phosphate. So the lithium iron phosphate, they tend to be quite, the open voltage characteristic tend to be quite flat. So you see that between the range 10 to 100% state of charge, the voltage does not change too much, while instead for an NMC, like the one that you would find on the recent Nissan Leaf and also a lot of other electric vehicles, the characteristic tends to change quite a lot, almost 1 volt of excursion between the minimum and the maximum voltage. Another important aspect to stress is that the maximum and the minimum voltage range, they are quite often set based on what's the amount of energy and what's the amount of degradation that you want to get or try to limit from your cell. Normally, it's the upper limit that affects the degradation. So the higher you go with the voltage, the higher the degradation accelerates. While for the lower voltage, you can go lower, but then the battery becomes kind of, it's deactivated, and then you need to re-energize it and reactivate. But normally, from a degradation point of view, unless you go very deep with the voltage level, is not as bad as on the other side of the spectrum. Now, why a battery is degrading? I mean, a battery is degrading because there is the transit of lithium-ion, let's say in this case for lithium-ion batteries, back and forth, and this of course creates some mechanical and electrochemical stresses on the different part of the battery. Now, it's a complicated business. Things change a lot depending on the chemistry. Not all processes are also well understood, but it's important, at least let's say from a high level point of view, try to have a good understanding on what are the key elements that characterize the degradation process in a battery, because as a matter of fact, knowing what are the drivers for the degradation can be a good way to define how well you should handle the management of a battery. So specifically, normally, let's say in the literature, we tend to identify two main types of degradation, one that we call calendar and another one that we call cycling degradation. And we try to identify different stressing factors like temperature, C rate, depth of discharge, the number of cycles, of course, that affect one type of degradation compared to the other type. In the literature, there are a lot of studies. The one that we took as a reference to tune our models are reported here in the slide. So the first one on the left side, it's related to the quantification of the cycling degradation. So the key message that you can get from this type of analysis is that the cycling degradation tends to have almost parabolic effect with a minimum between 20 and 30 degrees, where it's, let's say, the battery from a cycling point of view prefers to stay. And then if the battery gets too cold or gets too hot, then the amount of state of health that will be lost per cycle tends to increase significantly. The other characterization that we got is from this other work from the colleagues in Munich, where they cycled, or in this case they didn't cycle because this is just a calendar, but they basically kept at a given state of charge and at a given temperature different batches of cells and then measure the relative capacity over time. This is just an example on how the characteristic look like. So practically, if you look at the blue curve, you can see that for a series of cells kept at 25 degrees, after 10 months, at different state of charge levels, the relative capacity will go like this. Practically, it means that the lower is the state of charge at which you keep your cell, the smaller is the amount of health that you will lose over time. While the higher is the state of charge, the higher it's going to be the loss. And there is quite a monotonic trend in the sense that the higher the temperature of the cells get, the higher it's going to be the loss. Now, don't be concerned by these huge gaps. I mean, relative capacity 80%, it means that the battery has lost 20% of its life, which is the case if you basically keep a battery almost entirely fully charged and at 50 degrees for 10 months, which for an electric vehicle, this is definitely not the case. But it's important to stress that temperature for a calendar and state of charge play a very significant role in terms of degradation. Now, you can imagine the drill. In the moment that you have this kind of characteristics implemented, you can build models. And in the models, and you can use this characterization in order to quantify the amount of loss given the usage of your electric vehicle. So in this case, if you know the power profile either by charging or discharging, and if you know the temperature that has been kept, that the battery has been kept at, then you can quantify basically how much the battery will lose in terms of energy. So we perform a series of investigation. I'm going to report here just a few cases. One investigation that we carried out, for instance, was referring to quantification of the degradation while considering just the pure driving and charging behavior, and while considering a bidirectional operation like the one that I mentioned at the beginning, when we are providing frequency control, bidirectional frequency control during the night, evening and night, and considering different frequency patterns from Denmark, DK1, which would be continental Europe, Denmark DK2, which would be the Nordic system, and in this case, the Japanese Tokyo area frequency. And you see down below the expected capacity, so the residual state of health, after 5 years of operation. And you can appreciate how between the baseline, which would be the black curve, which is referring to pure driving situation, and the different cases where it's driving plus frequency service in the three areas, the gap is not so large, while the overall value tends to get much lower. So the residual capacity gets much lower in the moment that we keep the battery at a fairly high state of charge value. So what is the key lesson learned that we can take here, for instance, is that how well you handle your state of charge has a much more important implication from a health point of view rather than how much you utilize your battery. Again, we have to keep in mind that this is a vehicle, it's not a stationary storage, and electric vehicles tend to cycle way less than what a stationary storage would do. That means that even though you are having your vehicles experiencing a fairly stressful operation like this frequency service for 14 hours per day, still the additional degradation that is caused by that, even though it's non-negligible, it's still not so dominant compared to the degradation that you would have anyway, simply because the time is passing or because you were not too cautious in handling the state of charge. Now, one can also get a little bit more creative, and then you can have some sensitivity analysis just to get an understanding on how you could, how could the model predict the different type of degradation depending if you are cycling the battery and keeping the battery always at 25 degrees, which is also an ideal case, and then depending on whether you are cycling half, 1/4 of a cycle per day, or half a cycle per day, or 2 cycles per day, you can get after 10 years of operation how much is going to be the residual state of health. And then you can appreciate how in this case keeping the battery at 10 degrees or colder temperature is of course more stressful from an cycling degradation point of view. The formulation is quite straightforward, the one that we discussed in the paper, so you find it reported here in case you want to implement it in a simulation environment. It's also quite interesting to stress the sensitivity on the calendar, and you see here a similar chart. So over a 10-year period, when the battery is kept at 25 degrees, which from a calendar is of course worse compared to keeping the car at 10 degrees, because the calendar tends to accelerate when the battery is warmer. And you see here the different curves if the car was kept at different state of charge values. So the one on top, for instance, refers to a very low state of charge, like 45%, while the one below refers to fairly high state of charge values, like 85 or 95%. Also, in this case, the analytical implementation is fairly straightforward. It's just this integral equation that you find it here. Now, wrapping up and getting towards the final part of this tutorial, we have been having this measurement of capacity of the car, and we have been having also these models to quantify the degradation of the car. We have been trying to match, of course, also the measurement that we did ourselves with the models, and try to see whether let's say the expectation of the model matches with the reality of the measurement. But one thing that we came to realize when performing this kind of test is that according to the IEEE standard 62660, as a matter of fact, there is no universal definition of rated capacity. That means that how much is the initial capacity of your battery? It's something that each manufacturer defines independently one from the other. There is no universal way. That means, for example, just to give a simple view, if you take the NMC characteristic that we presented previously and you decide that your minimum voltage is going to be at 3.4 volt, or if you decide that your minimum voltage is going to be at 2.8 volt, then you are adding a 5% energy level, state of charge level between the two limits. And of course, it's up to the battery manufacturer or to the BMS that is set by the car manufacturer to define this kind of voltage limit. And to make things more complex, this voltage limit can also be changed over time, as a matter of fact, to alleviate the perceived degradation. So it's a common practice from some car manufacturers that they start with a certain minimum voltage and then they shift the minimum voltage over time so that you can reduce the effect of the degradation. This, of course, makes, let's say, life a little bit more complex when you try to quantify the degradation, because then you are mixing up two different things. Now, the last thing that I wanted to tell you about is basically putting together all the different things. So I've been carrying out this kind of investigation also on my own leaf over the last 3 years. And what I did was basically to put together the onboard data that was acquired by the leaf spy. So in terms of time, state of charge, kilometer, and temperature, use this data to feed the degradation model that I described previously in order to derive an expected state of health model. Out of the onboard diagnostics, I also retrieved the state of health reading. And then finally, I compare with a third state of health estimation that we derive when we perform this measurement, this capacity measurement in the lab. The capacity measurement, as a matter of fact, it consists in completely discharging the battery of the vehicle and then charging it at a very low C rate and monitoring practically the energy that we are charging up into the car. And then in the end, we have been comparing the state of health obtained by the different measurement or model or values. Just to give you some context, I drive on average 45 kilometers per day. It's mostly, let's say, commuting or small tours, but there has been also a few days where I had some long journey. So it's a little bit of a standard driving behavior according to the European driving styles. So far, the battery has experienced approximately 130 full equivalent cycles, and of course I've been keeping track of temperature, state of charge, and so forth. An example of onboard reading, so what the kind of measurement that we get. This is the Leaf Spy. If you have been working with the Leaf, is of course a very popular app that gives, basically it's sniffing the CAN bus measurement, and you can get quantities like the individual cell voltage, the temperature, power, and so on. So when we perform this kind of capacity measurement, for instance, we completely discharge the battery, and the BMS basically stop any further discharge in the moment that the first triplet of cells reach the minimum voltage, which is around 2.85 2.83, 84 volts. At this point, you can't discharge anymore the battery. And then when the battery is charged up, of course, the voltage rises. And when it's around 4.2 volt, that's where you have the topping of the battery. This is an example of a full charge where you see the current. It's around 23 ampere, which is more or less a C rate that is 1/7, so it's not too large. You have the voltage, you have the state of charge, the power, and of course the temperature over the charging session. And finally, this is a comparison between the output of the model, the measurement activity, and the capacity. So practically in the first 3 plots, you see the historical data that I used to feed the model. You have in green the air temperature and in black the battery temperature. You can recognize these spikes where when the battery is, of course, experiencing a repeated sequence of fast charging. That was during some long journeys. The historical state of charge values on a daily basis, and the odometer, meaning the kilometers that have been driven over the last 3 years. And down below you see 3 curves. The blue one, it's the state of health provided by the battery management system, so it's the one retrieved by the leaf spy. The one in red represents the state of health that is estimated by our models, and the green circles with this tolerance band, they represent the capacity measurement that we perform in the lab. So far, I would say everything is going as expected. So there is a trend, degradation trend that is going as expected. It's quite interesting to notice that the BMS has, of course, keep tracks on a daily basis on the state of health. But then every 90 days, there is, let's say, a major refreshing of the algorithm. So the algorithm decides whether to, let's say, round up or round down the estimated capacity of the battery. One important thing that I want to stress is that it's important, again, to take into account what's the reference energy that we are taking to set the initial capacity. So in this case, for the Leaf E+, the nominal battery pack is 61.8 kilowatt hour, which I assigned as 100% state of health. But it's important also that to remember that the car is actually sold with a usable capacity of 56 kilowatt hour. And so far, the capacity that I measure is around 58. That means that from, let's say, the end user point of view, the battery has still more capacity than what it was sold for. But it does not mean that the state of health is going to be more than 100%. It's simply that it's going to be larger still compared to the net capacity, because the gross capacity was larger than the net. Finally, I want to wrap up with one final consideration, because I've been talking about degradation, I've been talking about V2G provision while providing frequency control. And at the beginning, this has been quite an interesting use case, but it does not mean that from a frequency, that from a bidirectional point of view, that's the only operation that it can be performed. For instance, starting from this year, here in Denmark, it became quite interesting also another type of service, which is more based on a time of use. Practically, the idea is to take advantage of the fact that in Denmark, between 5 and 9 in the evening, the utility charges a very high fee because they don't want people to consume too much during the evening, the so-called cooking peak. So practically during the winter months, so between October and March, the utility charges, and that's the orange bar that you see here, a very small fee between midnight and 6, a medium fee during the daytime and late evening, and a very high fee, a consistently high fee, between 5 and 9. Then on top of that, we have the fee that the state gets, so it's an energy fee, plus the VAT, which is also something that the state will get. And this is pure fees from the utility, from the state, or again from the state in terms of VAT. And this goes on top of the spot price, which of course is variable throughout the day. And quite interestingly, the spot tends also to be tends to be larger during the evening peak. So this effect gets also amplified because the spot gets larger during the evening time. That means that this large delta, which assuming a spot price equal to 0, it's still quite consistent because it's around 24 euro cents per kilowatt hour between the night price and the evening price would be a very interesting time of use case for a bidirectional system, for a vehicle to home system in this case, where practically we could take advantage of charging during the night and then covering the consumption during the evening. So not necessarily selling into the grid, but just covering the local consumption. Clearly, if you have a photovoltaic during the day, that's could still be used, and then instead of charging during the night, you could charge during the day with even cheaper electricity, and then covering the consumption during the evening. The numbers, of course, can change quite a lot depending on the specific situation, but we are talking a few €100, which clearly go up with the amount of energy that you can cover, that you need to cover throughout the night. But the advantage, for instance, compared to the previous frequency case is that this is a purely behind the meter operation, so you don't need, let's say, anyone to take care of your, you are not committing your car into the market. You are just doing, let's say, your own business behind your own meter. And that means that you can do it whenever you like. You don't need to participate in a market, and you don't need anyone that is let's say, taking care of your electricity production. So it would be much slimmer as a setup. Let's see if this one will become quite popular also elsewhere, and if it will really become a killer app for the bidirectional charging. Now, I would like to wrap up this tutorial and just the key takeaways that you find summarized here. So the profitability, a few years ago, it started to be quite interesting from frequency service, but you need to remember that there are some losses associated. You need to participate into the market and so forth. The management of the state of charge is, of course, quite important. The good news from a degradation point of view is that the degradation, of course, is not negligible, so it's still there, but it's not so large that really makes the business case looking too bad. And as a matter of fact, there are new services, or if you still want to participate to the frequency base, that are still quite interesting, like the containment reserve, because they are less impactful from a cycling point of view. There is this important gap that the definition of battery capacity and state of health is still very much arbitrary, so it's always important to understand how you calculated that number. And then the time of use case in Denmark is actually opening some interesting opportunities and revenue stream. In all cases, it's important to stress that also with this application, efficiency at low loading values remain very important, because otherwise you end up burning energy. And finally, it's not a small note, but it's an important note that so far the only V2G and V2H application commercially available are through the CHAdeMO protocol, and it's been still under development, this kind of implementation with the CCS. So now we are starting to see some pre-trial, but it's still not fully operational yet. You find some references here, and with that I'll conclude my tutorial, and you have my contact, so if you have any question, feel free to write me. Thank you.